So thank you, everyone. Today, my topic is an overview of configurators for industrialized construction. I'm going to talk about this topic from typologies, customer requirements, and technical approaches. I once worked for a design firm. They developed the timber panelized structures, mostly for educational buildings, and they used the configurators to support their design. At the same time, they also developed the configurators for other construction companies. So I worked for them for 2 summers, and the experience on the configurators development motivates me to start this topic this year at ETH Zurich. So this is a little bit background for myself. So let's start. From 2004, we can see more and more investors stepped into this industrialized construction market. Especially from 2018, you can see there's a drastically increasing investment, including the $1 billion investment from Google and $2.9 billion from Wake Company. And we can see the momentum behind those facts, and 22 billion, probably the 22 billion potential annual cost saving and 20 to 50% time saving, like are offered by this kind of industrial construction project, reported by McKinsey in 2019. So with some of the investment, there's an increasing number of startups. They are trying to develop this kind of digital platforms, or we call it the configurators here, for the industrialized construction project. Some configurators, such as the TestFit, Prism, and SpaceMaker, they are configurators targeting at the planning stage. And some configurators, such as the Project Frog, they are configurators focusing on the planning and design stage. And Katera, their vision is to develop our all-in-one integrated platform covering the planning, design, and the fabrication stage. So to give you a concrete idea, what is a configurator, I'm going to show you 2 examples here. So first example comes from the Project Frog. It is used for the timber panel structure design, and you can see from this web-based configurator, the user can arrange the spatial layout and the seat division for each room and place the structure and the non-structure panels, and also as well as placing the openings for their buildings. And in the end, the design will be automatically checked by the related building codes. And this is, so the second example comes from the TestFit. So this is a configurator for the planning, and the user can set the site of boundary on the map and swap and select the building types predefined in the system. And based on the also relevant constraint and adjacency rules, the diverse floor plan schema can be generated. And in the end, each configuration will be evaluated by their cost performance and to support the decision-making process. So what is a configurator? So we try to define this concept, and we can gain some inspiration from previous study. And here I just summarize some key features. So first, configurators can be used to generate the derivative products based on a set of common modules or components used by past project. And second, it is an expert system embedded with the predefined product specification, or we call it the configuration rules here, which constrain how those modules or components get assembled together. And in the end, it is definitely a software with high automation, and which requires a minimum of data entry from users to achieve the product variations. By studying the existing configurators, we find out there are 2 motivations that drive the application of configurators. The first is this kind of mass customization. So nowadays, customers, they want to buy cheaper products. They also want to have products more suitable to their personal requirements. And so by using these configurators, it eliminates the inefficient conversation between the clients and designers. And the second motivation is this kind of 2-direction feedback loop. So in the past, information can only be transferred downstream in one direction, and it might cause the problem that the stakeholders on the upper stream, they have little knowledge about the feasibility or financial performance of the solutions. So the configurators try to solve this problem by embed those rules and constraints from downstream and transfer it to upstream to guide the decision-making process. However, the application of configurators in industrialized construction is still limited and immature. Firstly, existing configurators do not satisfy the requirements for the industry practitioners from different trees. And we also find there's a lack of comparison between the similarity and difference in configurator approach. So consequently, without a clear knowledge of the configurator-based workflow, we find that many companies, they are not willing to apply configurators to the projects due to the uncertainties and the disturbance on their original project delivery process and technical environment. So to solve this problem, we try to answer 3 fundamental research questions. So first, what are strategic typology of configurators for IC? And what are stakeholders' requirements, and how each typology of configurators attempts to satisfy those requirements? And also considering the development application of configurators are interlinked, we try to briefly summarize the technical approaches to develop those configurators for IC. So the data source we use for this review come from the 2 parts. The first, we collect academic literature, including 9 journal papers and 2 conference papers, and you can see the keywords and the targeted domain we focus on there. And also to supplement this review, we also collect the real commercial software, the 4 commercial configurators, which have the demo and the free trial version for our testing. So based on our above cases, first we generalize 3 typologies of configurators from 5 perspectives. Who are the main users for each configurator? And when are configurators used in the project? And what key activities performed by configurators? And what targeted products are suitable for configurators? As well as what expected output are generated by configurators. The second step, we categorize the requirements of stakeholders from the clients, designers, manufacturers, and assemblers. We further demonstrate which requirements each typology of configurators try to achieve. And last but not least, we apply this 3-tier software architecture decomposition strategy to study the technical approaches for the development of configurators, namely the presentation tier, application tier, and data tier. So our first finding is strategic typology of configurators. How is it implemented in the project? So the typology 1 represents configurators in the conceptual planning stage. The main users include the planners, developers, and architects. The major output, the objective is to generate the diverse site plan, the building shape, and the floor plan schema, and etc. To achieve those goals, those configurators need to embed the site data, the urban planning regulations, the geographic data like the wind, the sunlight. So the output could be represented as a simple geometry or a wireframe. We find there's a limitation to convert those low-level detail web representation to the BIM object to further support the design development. And typology 2 represents configurators for the design stage, and the targeted products include the prefabricated parts, assemblies, and modules. And the expected output include the permit drawings, the prefabricated models, the manufacturing bill of materials, and as well as the operational codes for the equipment. And typology 3 represents configurators which has not been widely achieved in the commercial world. Related research work has been done in the design for manufacturing assembly domain, the DFMA. And generally speaking, it is like, so this kind of tool try to optimize the design based on the DFMA principle proposed by the manufacturing industry, for example, such as reducing the number of unique parts to achieve the production efficiency. So this is an example of typology 1 configurator. And it offers planners with multiple site layout by taking the building performance into consideration, such as the energy efficiency, the daylighting, and surrounding noise, and etc. And this is a type 2 configurator. It is built upon the existing BIM application, the Revit, and it is used to generate the fabricated model as well as shop drawings. And to support the selection of configurators, we further match the above 3 typology of configurators with requirements from clients, designers, manufacturers, and assemblers. Here, I just clip a part of result from my paper. And some specific takeaway include typology 1 configurators need an accurate and timely estimate for total cost and delivery time. Because it is usually the case at the early stage of the project, there's a limited input. And typology 2 configurators we find it is most widely used one in the industry. It is aimed at automating the professionals' work, such as those repetitive modeling work, but with limited flexibility to suit new products design and new constraints for different project setup. And typology 3 configurators, as I said before, is less achieved in commercial world, and we find there might be two reasons. First, those factories, they have their own production system which directly control their equipment, and also there is a lack of metrics to measure the manufacturability or assemblability of the design. And last but not least, we find some functionalities, we summarize it here, has already exceeded the definition of configurators proposed by manufacturing industry. And we find the reason could be the AC industry are so fragmented, so multifunctional and integrated configurators are required by all stakeholders. And finally, we did a brief review on the technical approaches to build these configurators. And you can see we use this kind of three-tier architecture. And on the presentation tier, we find that the user interface enable a different level of freedom for non-expert and expert collaborative design. So according to different project complemented specification, namely the engineering to order, modify to order, configure to order, or select variant, the enabled interaction on the interface include allowing the users to define the constraints themselves. They can arrange a spatial layout. They can just edit the parameter value or select the predefined kit-off part. And on the application tier, multiple functional modules are established, and they can visit the data tier, the BIM model by using the API request. And in our paper, we illustrate how those configuration knowledge, configuration rules could be formalized such as the constraint satisfaction problem or the shape grammars in the production planning module. So as a summary, the configurators are emerging, and more configurators are released and applied to the industrialized construction project. And in our review, we find that there are 3 typologies of configurators and the corresponding requirements from stakeholders. And we also find, just like other lightweighted web-based applications, the configurators share the same software architectures. As for future work, we propose a roadmap for the research on configurators. First, how could client's intent be translated into product's property and further linked to the module or combination of modules? And second, how could relevant data and regulations be efficiently embedded in the configurators to assist the design, generate the design and validate the design? And more importantly, it needs to be easily updated for future projects with different setup. And thirdly, how could artificial intelligence support the expanding and more importantly, guiding the design space exploration, considering the design is a sequential decision-making process and with the input are added progressively. And last but not least, how could digital fabrication, such as the 3D printing, robotic manufacturing, support the free-form module parts development? And this might require a better understanding on the limitation of those new equipments imposed on the design. So briefly speaking, there are 4 dimensions of research on configurators: formalization, automation, generalization, and integration. This is the end of my presentation. Thanks for your patience, and I'll continue your questions.